Good morning. Well, this is a little review for the topics of the phase diagrams. These are the Hume conditions, the Hume Rottery conditions for total solubility in alloys. The first, the size factor. Remember the difference in size, less than 50%. Then the crystalline structure is crucial. So if you have different crystalline structures, the solubility will be possible only in low concentrations. The balance, if the materials share the same balance, it's possible that they they coexist in the system, but difference in imbalances make the materials react. And finally, electronegativity. It's important in a couple of materials that don't share the same region in the periodic table. For metals, this doesn't matter because the bond is always metallic, but couples of semi-metals and metals, it matters. The difference in electronegativity and the polarity appearance make that the material react and the compound segregate from the structure. Well, you did some exercises matching a pair of materials and decide if this new alloy it will be soluble completely, partially, or at low concentrations. Following with the lever rule, this one in some courses I explain it, in others we have problems with the connectivity, so I will explain again the exercise. The lever is sketched here. There is a pivot and the lever has two sides, the short and the long, and in an alloy that is in solidification, usually we want to know how much is partially solidified, and inside the solid region how much exists in a given phase. So let's move to a phase diagram. For example, this one, the binary diagram for brass, zinc, and copper. And what we want to do an isoplethic explanation of solidification. Isoplethic is to follow at a fixed composition what happens along the solidification pathway. So let me change and draw. Let's change the light and draw some arrows. For example, here. The question could be how much alpha phase exists here at this and at the orange ball, and the isoplethic path is the total solidification pathway. So the solidification occurs passing from the liquid to the solid, and then crossing all the phase lines. So I want to paste another point here on the liquids. So the description of the isoplethic path is at 1100 Celsius the material is liquid. Then if you cool the material and you pass close to what's that value, 1000 Celsius, the material solidifies. And this brass, this composition, more or less 50% of zinc in this binary diagram. This axis contains here at left the total, the whole copper, and in the opposite axis the whole zinc. So from left to right, increase the zinc content. This scale is for the zinc content in mass. So here more or less we have 15%. So a 50% of zinc in this brass. The material is liquid above 1000 Celsius. At 1000 Celsius solidifies. If we make a stage or a step in annealing or quenching, what if we stop here at 700 Celsius? So if we stop here at 700 Celsius, I want to know how much alpha phase have we. On the left side, we have complete or entirely alpha phase here at 0. And when you touch one phase line, this curved line, disappear the alpha phase and appear the next, for example, beta. So here you have 0 alpha and appear the new phase. The new phase that could be, let's call it beta. Well, so at this point, I understand that you got that the alpha is on decreasing. So if you want to know the amount, we can do these calculations. So first, try to read the values on the limit of the region. For example, what's the value here on this line at 700 Celsius? More or less 38, 39%. Well, I think it's less than 39, maybe 38% zinc. That's the value here on the phase line. And we need the value here on the pivot, 50%, and the initial value here is 0. Okay, 0. So the calculations will be alpha, amount of alpha at 700 Celsius. It's the ratio of the concentration of material at this point divided the total concentration. Well, what's the total concentration? Here, if we extend the value, that's the total. So the Lever rule says that the mass of beta appearance will be the green line, the green arrow, divided the blue arrow. Okay, the green arrow has a value of 15 minus 0. 15 minus 0. So in other words, is 15. So 1 minus, and the ratio 50% of zinc divided the total length of this segment until the phase line change 38%. 38%. Well, so only we have to do the ratio, the arithmetic operation. So this is 1 minus, and the answer for the ratio here is 15 divided 38. This answer is 0.394. 0.394 using only 3 decimals places. And if we follow the arithmetical operation, the answer is 1 minus this value, so 0.60. 0.60. That's the fraction of alpha. Why? Because we are calculating the advance on zinc, and the zinc has another structure. So at 700 Celsius, the alpha crystalline concentration is 0.605. What if we move to the next arrow? So what if we are now here? You cool the sample. It's clear from the TTT lessons that as you cool, it's possible that some phases appear and another disappear. So at 200 Celsius, what's the crystalline alpha phase concentration? 200 Celsius. Well, again, the segment from left to right disappear alpha and appear beta. So if you want to know alpha, you must subtract to 1 the fraction that explain the appearance of beta. So again, we have 15, but now we have another value. What's the new value? if I move the arrow here at 200 Celsius, I think is 35% of zinc. So I change here the answer 35, and this give me division. I am using my calculator to solve this answer. Dividing 35 is 0.428, and the subtraction 1 minus this ratio 0.5771. So we demonstrate again that as you cool, it's possible that the concentration of crystalline phases change. Well, what if we do the exercise inside another region and you develop another isoplethic analysis? What if the concentration of zinc increase until 50% here, 50%, and you do exactly the isoplethic behavior? So in the next line we have 0 beta and 100 gamma, the next crystalline structure. So the only what we need is to place, for example, any value that what's the concentration of crystalline phase gamma at this point. So we start from the beginning of the region, that's the beginning of the region, and the total distance in the region, that's the total distance. And you read the values here. So for the beginning and for the end, the new values will be what do you think, 41, 42? Let's use 41. Okay, and for the end of the region, sorry, in the middle we have 50. Here we have 50% of nickel. Yeah, and at the end of the region, let's read the next value, and according to my eye, in the middle 50, 54. Okay, 54. So let's obtain at 800 Celsius now the amount of beta. Beta, because we are cooling here at 50% of zinc composition. So 1 minus, and we need to do new calculations. So on the denominator we have the subtraction, the pivot is 50 minus 41, 50 minus 41, divided the total length, 54 minus 41. Okay, well, doing the calculations without step by step. So let me do in my calculators. 1 minus parenthesis 50 minus 41, close the parenthesis, divided parenthesis 54 minus 41, and again 0.30, 0.30, 0.07. That's the percentage of beta. If you move the point along the isoplethic pathway, you find that close to 550 Celsius, beta disappear and the material pass to the next region. So we need to do the calculations inside the next region to obtain the crystalline phases that you are obtaining as you cool the material. Well, this is a review for the isoplethic analysis. Remember, an isoplethic analysis is the description of cooling at constant composition. Please review and try to guess other exercises by yourself. Bye.